So welcome back. This is our third video about the variable elimination, and now we will continue discussing the idea of the width of elimination order. So now we're going to define a new graph that's called an iteration graph. An iteration graph is an undirected graph that has the same variables that we have in the Bayesian network. So for instance, we have this Bayesian network here, and we will create an iteration graph for this Bayesian network here. So we copy the same nodes, so we have the same variables, and we connect two variables together if they appear in the same factor. So these are the factors that we have for this Bayesian network. So we can see that we have this factor here, theta a, that only has variable a, that's fine. We have this factor here that mentions variable b and a, so we need to connect them with an undirected edge. We have a factor that mentions c and a, so we have to connect these two variables together, and we have this factor here that mentions d, b, and c, so we need to connect them together, so we will do this. And finally we have this factor here that mentions e and c, so we need to connect them together. So this graph here on the bottom is very similar to our Bayesian network, but we have one more edge, and it appeared because of this structure here that we have the V shape. We have this convergent structure, and we created this link here connecting these nodes B and C. We call this process modalization, so it's going to be like modalization, and yeah, it's a strange name. Basically what we are doing, we are marrying the parents of a common child, so that's why people use this term. We can also think that the variables in a factor fi, they form a clique in G, and the clique is a graph that is fully connected, so we have edges between all variables together. So yeah, it's the same process as I mentioned before. It's very similar. So the only difference here is that again, we have a clique over a, that is just a. We have a clique over two variables b and a, and there's going to be a connection between b and a. We have a clique for variables c and a. Again, it's an indirect edge connecting these two variables, and the only difference is going to be here, where we need to make a clique over variables d, b, and c. And in this case, we'll have to go here and say, okay, in order to have a clique here, we need to connect this variable, and this variable together. So we're going to have this small clique here. For e and c, it's going to be just an edge connecting these two variables together. And we can track how this interaction graph changes as we eliminate the variables. So let's suppose that we have this elimination order here, B, C, A, D. And we have this iteration graph for the Bayesian network that we created in the previous slide. So we're going to eliminate the variable B. And as we eliminate the variable B, we do the process that we know. We take all the factors that mention variable B and eliminate that. The resulting factor, we're going to be this factor here, F1, that mentions variables A, C, and D. So if we look at the new iteration graph, it will not mention variable B anymore because we eliminated variable B, but it will have a factor that mentions variables A, C, and D. So you're going to have this new edge here connecting A and D. Remember that because we have this factor A, C, and D, we need to have a small clique that mentions those variables, so we have this clique here. And we continue. The next variable that we're going to eliminate is going to be C. Okay, C is this middle variable here, and we need to eliminate that. When we eliminate C, we create a new factor, F2, over A, D, and E. So we need to connect this with a clique again, so we're going to create this new edge here that it didn't have before. And we keep in doing that. The next variable we're going to eliminate is A. So A is here. We eliminated this variable. We're going to have a factor that mentions D and E that are already connected together. And finally, we're going to eliminate the variable d, and the resulting factor will only mentions variable e, that is here. So we can understand this process. Let me erase this in a graphical way. That maybe is going to be simpler to think about it. And in this process, we can think that when we eliminate one variable, we're going to connect together all the neighbors of that variable. So we start eliminating b, right? And b has those neighbors here. It has a, c, and d. So when we eliminate b, we're going to connect them together. But A and C are already connected, and also C and D are already connected. The only new thing that we need to create is an edge that we're going to connect A and D. So now we have A, C, and D all connected together. The same thing happens when we eliminate C. C has three neighbors, A, D, and E. When I remove C from here, I will need to connect all those neighbors together. But A and D are already connected together. We will need to create this new edge here connecting D and E, and the new edge here connecting A and E. So we have this new graph here. Again, I'm going to eliminate A. When I eliminate A, I will need to connect all the neighbors together, but the neighbors are already connected, so we do not create any new edges here, so we just move to here. And when I eliminate D, again, we have just one variable remaining, and so we don't need to create any new edges. So great, in this slide we have a little bit the formalization of this idea. So we can think about a series of operations over these interaction graphs where we eliminate one variable at a time, and we start with the model graph that we created from the Bayesian network, and we start eliminating one variable at a time. So we think that we start with a model graph G, and we start operating over this model graph and eliminate one variable at a time. We can think that we will create a sequence of interaction graphs. We just have to remember the two rules, right? So the first one is that when we eliminate one variable, we're going to connect all the neighbors that we have in this variable in the graph. We're going to connect them together. And after I connected those variables together, I can eliminate the variable pi from the elimination order. And we keep in doing that until we have just the variables that we are interested in the query. Okay, here we have one algorithm that uses those interaction graphs in order to compute the width of one elimination ordering. So we have done this before, but using a sort of a simulation process, thinking about the factors and the eliminating variables and the factors and keeping doing that. We can do a very similar process, but just thinking about the interaction graph. So the algorithm is the following. So we start with a Bayesian network N and the variable ordering pi. So at the end, you're going to return the width of this ordering pi. So I'm going to take one ordering as input and output one number that represents the width of this ordering. So it's going to be proportional to the quality of this ordering, and we are interested in finding the ordering that has the smaller width. But this algorithm will just measure the quality of a single ordering. If we want to compare multiple orderings, we have to run this algorithm one for each ordering and comparing the numbers later. So we started with the interaction graph that we created from the CPTs of the Bayesian network N. So this graph G here is the model graph that we create. So we needed to connect every pair of nodes that represent a variable that appears together in a factor. We initialize the variable w that we will return at the end of the algorithm with the value is 0. And we iterated through the elimination ordering here, pi. For each step, we're going to take the maximum between w, that is initially 0, and d. And d is the number of neighbors that I have for the variable pi. So this is, when I is 1, this is going to be the first variable that I'm going to eliminate. So basically what we are doing, we are measuring the number of factors that we have when we multiply all the factors that mention variable pi together by counting the number of neighbors that this variable has in the interaction graph. And I'm going to connect using an edge every pair of non-adjacent neighbors of pi in G. So this is the process of creating the cliques for every neighbor that we have for the variable that I'm going to eliminate in G. And I can eliminate the variable pi from G, and I keep doing this process and repeating that for the second variable that I have in the elimination order, the third one, until I finish with the elimination order. So again, this is the same algorithm that we did before, but now we are just looking at the interaction graph. One application for this algorithm is to measure the quality of an ordering before I use it. So I may select the ordering. I want to know if the ordering is good or not. I can measure the width of this ordering using this algorithm. But you may think that, okay, we could take all possible orderings and feed each of these orderings to this algorithm and take the best one. But there are n factorial possible orderings for n variables, so that is not a feasible approach for solving the problem. We need to use something different, and we're going to discuss that in future slides. So we have some bad news here. It's saying that computing the optimal ordering is an NP-hard problem. So it means that in worst case, it's going to be exponential in time. So yeah, finding this optimal ordering may be very hard to do in practice. But what we can do is to use some heuristics in order to get a good ordering, something that will work in practice and will give us the final result in a reasonable amount of time. And there is one heuristic that is very popular, is very simple to implement. It's called the mean degree heuristic. The idea is that if we take the interaction graph, right, and we want to eliminate the variable a, we're going to compute the degree of this node a and take the node that has the smallest degree, the minimum number of degree. Because we know that if we take a, we're going to have to put together all the variables that appear in factors that mention a, and these variables will be the neighbors of a. So when we eliminate a from here, we need to connect all those nodes together, meaning that we have a factor that mentions all those variables. So we're going to locate the variable that has the minimal degree, and we'll select this variable first. We will compute a new interaction graph. I'm going to select the next one that has the minimal degree, and that's going to be my second variable to be eliminated. And I keep on doing that until I eliminate all the variables. Look at that, this is one heuristic. It means that it can work, frequently give us some good results, but it's not guaranteed to give us optimal results. So basically a grid algorithm that selects the variable that has the minimal degree in the interaction graph. So we know that for some very contrived, very small cases, for instance, when the elimination order that's optimal has the width that is less or equal than 2, this heuristic will give us some optimal results, but in the general case, there are no guarantees. So let's take a look on the algorithm so we can formalize this idea a little bit better. So this is the algorithm for computing an elimination order based on the heuristic mean degree. So we call it the mean degree order algorithm. We take as input a Bayesian network n with the variables x, so x is going to be a set of variables. We return an ordering pi of those variables in x. So we start with the interaction graph that we created from the Bayesian network. We're going to call this graph G. This is basically the modal graph that we obtained from the network. And I'm going to iterate over all the variables in x. So for each step of this for loop, I will select as the variable to be eliminated the variable that has the smallest number of neighbors in the interaction graph G. And that's going to be my pi I variable. So it's going to be the first variable to be eliminated, and I need to update the interaction graph. But the process of updating the interaction graph is exactly the one that we described before, right? So we create an edge between every pair of no adjacent neighbors of pi. So I look for the variable that I'm going to eliminate, look for the neighbors, connect those neighbors together, and I delete the variable pi from G, and also from the set X. And I will go and iterate it one more time. Now I have the update interaction graph. I will select the variable in this update interaction graph that has the minimum number of neighbors, and I keep on doing that until I have eliminated all the variables that are interested. All right, this procedure works very well, but there is another one that usually gives us a little better results. And the idea of this second heuristic is that the best ordering is the one that creates the smallest number of fill-in edges. And the fill-in edges are the new edges that we created in the interaction graph as we eliminated the variables. Let's take a look on that. So the second algorithm, we call it the mean fill order, right? And this idea is that I should select the nodes first that introduce the smallest number of fill-in edges. So let's just remind what is a fill-in edge. So we had in our example a network like this, and this is the model graph for our Bayesian network. And if we look at this interaction graph and we start thinking about eliminating the variables, let's see what happens if we eliminated the variable A. So the variable A is connected with variables B and C. If I eliminate A, I will not create any fill-in edges because B and C are already connected together. So that's good. Let's take a look on B. If I eliminate the variable B, I will need to connect together A and D because I need to connect all the neighbors of B, and the neighbors are A, C, and D. And C and D and C and A are already connected, so I will need to connect one, we need to create one fill-in edges. So for A, I created 0, but for B, I will need to create 1. What would happen if I would think for the case of C? Right, so C is here, and if I eliminate C, I will need to connect the variables, well, every one, because C is connected to A, to B, to D, and to E. So in this case, I will need to connect A and D together. They are not connected. I will also have to connect D and A together, and I will have to connect E and A together. So in this case, the number of fill-in edges that I will have to create is 3. If we eliminate D, well, D are connected with B, C, and E, and as I eliminate D, we will need to connect D and E together because they are not B and E together because they are not connected. So in this case here, it's going to be 1. And for E, I do not need to create any fill-in edges because E is only connected to C. When I eliminate E, there is no need to connect anyone. So in this case, it's going to be 0. So for this graph, I need to do this simulation process to see what would be the fill-in edges created for every node that I could eliminate and figure out which ones have will create the smallest number of fill-in edges. In this case, my choice will be between A and E. And well, in the case that we have, like here, we have 2 options. What people frequently do is to use the mean degree to untie this. So we're going to select E first. But it's just one heuristic, but it's very common to compose mean fill order and use mean degree to solve when we have those ties. So the mean fill order algorithm is very similar to the previous one that we saw, the mean degree order. We just replaced the idea of selecting the variable that has the minimal degree by the variable that is creating the smallest number of fill-in edges. Okay, I guess that is enough for this video. and we will continue in the next one, discussing how we can compute posterior marginals. So see you in the next video.